Assalamu alaikum dear students. Today our topic is speed of sound. So by definition, speed of sound is the distance traveled by a sound wave in unit time is called the speed of sound. The speed of sound basically depends upon two things. The density of the medium. The speed of sound is directly proportional to the density of the medium and compressibility of the medium. The speed of sound is inversely proportional to the compressibility of the medium. So what exactly are density and compressibility and how it affects the speed of sound in a medium? Okay, first consider the density. Let's suppose we have a solid, a liquid and a gas. So in solid we know that the atoms are closely bound together, providing the sound wave enough medium particles to propagate through the solid. While in liquid we know that there are less atoms in as compared to the solids. So there are less number of atoms available for the propagation of sound wave. Similarly, in case of gases, very few particles or very few atoms of the medium are available for the propagation of sound wave. So what would happen? In solids, a sound would travel much faster. In liquids, the sound would somehow travel slower, and in gases, the speed of sound is the slowest. Now coming to the compressibility of the medium. The compressibility is in inverse proportionality with the speed of sound. Let's suppose again a solid, a liquid and a gas medium. Okay, here we take a solid and we know that when we apply pressure to any of its surfaces, it won't really compress. So the more the compressibility, the less the speed, or the less the compressibility, the more the speed. In the case of solid, the compressibility is very low, so the speed is very high. Similarly, in the case of liquids, the compressibility of liquids is somehow lower than the solids. So it's you can say it's the speed of sound in liquids is comparatively lower in liquids because its compressibility is higher. And in case of gases, that we know that the gases are more compressible than liquids or the solids. It's very much compressible. It's the most compressible state of any matter. Okay, so the more the compressibility, the least the sound speed. So in gases, the speed of sound will be very less than the liquids and solids because it has the most compressibility. Now you've seen how these two things affect the speed of sound in a material medium. Okay, hence the speed of sound depends upon the material at a given fixed temperature. Always remember that at a given fixed temperature, the speed of sound will depend on these two things. But at variable temperatures, of course, it depends upon temperature also, because temperature affects the density and compressibility of a medium. So, in turn, the temperature also affects the speed of sound. Now, coming to the mathematical equation, it's very simple. You've already learned about it. Speed equals to the speed of any wave equals to the distance covered by the wave divided by total time taken. V equals to S by T. You have already know that. So this was all about the speed of sound. Now coming to the speed of sound in air. We take for reference the speed of sound in air. Okay, so basically we calculate it in air because air is the most abundant space available on Earth, okay, above the surface. Okay, now as the temperature affects the compressibility and density of the medium, so sound is different for the same medium at different temperatures, as I said earlier. For air, at room pressure or atmospheric pressure, the pressure under which we are sitting right now, which is 101 kPa and 0 degrees Celsius. There are two basic conditions. The temperature should be atmospheric pressure and the pressure should be atmospheric pressure and the temperature should be 0 degrees Celsius. The speed of sound in air is 331 meter per second. Okay, so at 0 degrees Celsius, at 101 kPa, the speed of sound is 331 meter per second. So easy. With each degree rise in temperature, the velocity increases by 0.6 meter per second. So here comes mathematics. Velocity will be equal to the temperature at 0 degrees Celsius. Okay, the speed at 0 degrees Celsius. The speed at 0 degrees Celsius is 331 plus the speed at any given temperature. Let's suppose we are going to calculate temperature at 20 degrees Celsius. 0.6 is the factor which should be multiplied by each degree rise in the temperature. So if we want to calculate the velocity of sound in air at 1 degree Celsius, let's say, we will put 1 here instead of t, 1 multiplied by 0.6. So 0.6 will be the rise in 331. Or if we have 2 degrees Celsius, so we will put 2 here, 2 multiplied by 0.6, and that fraction should be added to 331 because that's 0 degrees Celsius. Okay, so we were just gonna put 20 here in place of t, multiply it by 0.6 and add it to 331, which is the velocity at 0 degrees Celsius. We will get the velocity at room temperature. Remember that whenever you get to find the velocity of sound in air at any given temperature, we have taken to 20 degrees Celsius as an example, but you can put any temperature you like, any temperature at which you want to find the velocity of sound. You can just put it up here because the temperature would rise, the velocity would rise at 0.6 meter per second only. Okay, so any temperature, each degree rise in temperature would give 0.6 degrees rise plus the velocity at absolute at 0 degrees Celsius. Now the last thing to note that is that remember the velocity of sound at a given temperature at a given pressure is same for each medium. Like for iron, let's suppose for iron we have 440 meters per second. Let's suppose I don't know what exactly is this value, but let's suppose for iron we have 440 meters per second is the speed of the sound. Now, no matter what the frequency is or what the wavelength is, the sound in iron at a given temperature, at a given pressure, would travel at the speed of 440 meters per second, no matter if it travels with a higher frequency or with the higher amplitude or both in the intermediate region. Okay, it will travel a certain distance in say 1 second. Look, here, here. It basically travels the same distance. Let's say if it is 0.5 6 meters, 0.6 meter, 0.6 meter. So in all three cases, the sound wave has traveled 0.3 meters in 1 second, 0.3 meters in 1 second, 0.6 meters in 1 second. So the speed remained the same. If the frequency increases, the wavelength decreases. If the wavelength decreases, frequency decreases. And if both are intermediate, then it's totally okay with it. So we can also take the case of water. Similarly, if we have a wave like this or a wave like this, or a wave like this, these three of the waves will travel the same distance in same amount of time. If the frequency varies, the wavelength would cover it. Okay, so let's take an example. Here we have the equation of the wave. We've already studied that. V equals to f lambda, where v is the velocity of the wave, f is the frequency of the wave, and lambda is the wavelength of the wave. Let's take an example. If v equals to 2 multiplied by 3, 2 is the frequency, 3 is the wavelength, let's say, then v will be 6. It is important to be noted that for a given medium v should be constant. Okay, so 6 equal to, if this frequency changes to 3, what would happen? The wavelength would turn into 2 in order to keep this velocity constant. Okay, so basically the velocity remains constant for a given temperature and a given pressure. Thank you so much everyone. Good day.